есть только небольшое предисловие. Sorry, I'm in Russian, I explained something about. В следующем семестре мы в целом планируем продолжить работу этого семинара. Меня, правда, не будет, то есть я, может, и буду приезжать, но то есть в феврале точно у нас там каникулы есть 10 дней, в апреле большие есть каникулы, в общем, посмотрим, как пойдет. Но мы с Сергеем Галкиным сейчас обсуждаем, возможно, как бы план работы семинара на следующий год. Он будет в основном здесь будет, и Андрей Левин, я надеюсь, подключится. Вот. Подумайте, если у кого есть желание выступить на какую-нибудь тему, которую вы можете предложить, то мы с удовольствием вас послушаем. То есть это не обязательно должны быть чисто автоморфные формы, это роль не играет, но в каком-то смысле связанные с автоморфными, пожалуйста, с автоморфными формами или их какими-то приложениями. Это могут приложения какие угодно. Там, геометрии, топологии, не знаю, там, Валк-Брехли, дифференциальной геометрии, матфизики, роли никакой не играет. So, and today I'm happy to present you my colleague and my friend Neil Scheithauer from Darmstadt. He came to mathematics from physics.
Yes.
So, but your first dissertation was in mathematics, but diploma maybe was in physics, no?
The PhD was in physics.
The PhD was in physics, so you see.
And I forgot most about it.
But this is not important. This is a very good example of migration of researcher from physics to mathematics and from mathematics to physics now. So, you know, he works in the field of Borcherds Automorphic products and vertex operator algebra. And Darmstadt now maybe the largest center for studying automorphic form and especially Borcherds automorphic product, because Jan Brunier has position there. Niels worked some years in Edinburgh, and now he came back to Germany, and he's professor and at the moment dean in Darmstadt Technical University. And so today we have a good chance to listen and to follow one of the best specialists in this area. Moreover, on Thursday, on my special course in the 17 o'clock in 2007, I think, Niels gives a general overview talk on the Weyl representation. We touch this subject a little bit during my special course, because this is a representation of Jacobi modular forms in terms of vector-valued modular forms. And Weyl representation is one of the main tools to study Borcherds automorphic product. So today we start the special subject, and on Tuesday it will be more, let's say, general talk, review about automorphic vector-valued modular form and Weyl representation.
Okay, yeah, thank you very much for the nice introduction. Yeah, thank you for the invitation. It's an honor for me to be here. So I will speak about Borcherds products of singular weight. Russia is famous for its excellent mathematicians and also for its seminars, which can take hours, I heard. So this will become important for us, because I prepared roughly 12 pages. So let us see how we can get through. Okay, so we start with the introduction maybe. So I will present to you 3 theorems, and the first one is the following. The first one gives a nice characterization of a certain Borcherds product, which is called phi 12, and I will explicitly write down this function later. So here I only give an overview of what we will do in this talk. So the function phi 12 maybe So this function is the only holomorphic Borcherds product of singular weight which you can construct from a unimodular lattice. So it's the only holomorphic Borcherds product of singular weight on a unimodular lattice. Okay, so this is theorem 1, and the proof here is not difficult, so it's easy to understand. So I will want to present this proof. Theorem 2 is a generalization of this result to lattices which are no longer unimodular. And here the statement is that on a lattice of prime level, you can have such holomorphic Borcherds products of singular weight only in small signatures. Yeah? And I have an explicit bound. So the precise statement is as follows. Take some constant c, which is bigger than 1 over the log of pi times e over 6, which is 2.83 and so on. So, okay. And you take such a constant c, then there's a d which only depends on c. And the properties are the following. So whenever you have a lattice of prime level, and signature n, 2, where n is bigger than 2. Okay, what else do we need? We need that it splits a hyperbolic plane. So this is a lattice of rank 2 of signature 1, and determinant -1. It's an even lattice. Okay. So then the discriminant form of this lattice is just the quotient, the dual lattice modulo the lattice. That's the discriminant form. That's a finite abelian group, and we call it D. So let D be the discriminant form of L. And now we suppose that this lattice carries a holomorphic automorphic product of singular weight. Borcherds product. I sometimes say automorphic product. Then we know that this n here is bounded, namely we have n smaller or equal times c times logarithm of the size of the discriminant group plus d. And the proof here is constructive. So we get an explicit bound for the signature. So we can take, for example, so you can take any c. What happens if you take c close to this boundary, then d gets very big. And if you go away from the boundary, then d gets smaller. You can take, for example, c equals and E equal to 40.52 and so on. So the important thing is that that these very special automorphic products, they can only exist in small signatures. Yeah, that is the important
Maybe,
statement.
I'm sorry, I would like to make some remark, maybe I can do it in Russian. So, сингулярный вес – это самый маленький из возможных весов для голоморфных модулярных форм. То есть для обычных SL2 модулярных форм или их конгруенс подгрупп сингулярный вес это будет вес 1/2. Для ортогональной групп сигнатуры N2 сингулярный вес это будет N минус 2 пополам. То есть, скажем, для зигелевых модулярных форм 3, 2 сигнатуры сингулярный вес будет по-прежнему 1/2. Для форм, скажем, сигнатуры 4, 2 сингулярный вес это единица. Это первый вес, для которых возможны голоморфные формы, любые, произведения Борcherds или нет. А здесь речь идет о построении форм наименьшего возможного веса, который будет произведением Борcherds. Знаменитая форма Борcherds φ12 как раз такая. Сигнатура 2,26, вес 26 минус 2 пополам 12. Но теперь речь идет не о унимодулярных решетках, а вообще рассматриваем любые решетки. Какого-то. Please.
Okay.
It's some clarification.
Yeah. Yeah, I will, so this is theorem 2. I will recall the definition of a Borcherds product in a few minutes, and I will also say something about modular forms for the Y representation. So this is just an overview about the 3 theorems that I want to explain. So in the last theorem is another classification result. So maybe I remove this. So theorem 3 is the following. There's a special class of Borcherds products, namely Borcherds products which have very nice zeros. So the Borcherds products which appear in Lie theory have the property that they have no poles, only zeros, and the zeros have order 1, and they are orthogonal to reflection hyperplanes. And these Borcherds products, they are called reflective, and theorem 3 is a classification result for such Borcherds products. Yeah, and the result is the following. There are exactly 15 reflective Borcherds products of singular weight on lattices of prime level. And I have a full table, so I will write down the table at the end of my talk. Okay. Maybe I say something. So I always assume that I'm in signature n, 2 where n is greater than 2. Okay. So these are the 3 theorems. I cannot prove all of them in detail, of course not, there's not enough time, but I will prove the first one. The proof of the second one has a similar idea, and I can prove some of the ideas I can show you some of the ideas which are necessary to prove theorem 3. So that is my plan for today. It might be a bit ambitious, we will see. Okay, so the first thing, so Borcherds products, these are special automorphic forms on orthogonal groups, and they are obtained as liftings of vector-valued modular forms. So we will start with, I will say a few words about vector-valued modular forms. Okay. I will remove this one. So we start with the discriminant form, and I call it D. I say in a few minutes what this is. So a discriminant form is a finite abelian group together with a quadratic form. Which I will write as Q, and it takes values in Q modulo the integers. Okay, and I will assume that the signature is even. The idea here is the following. Any such discriminant form comes from an even lattice. So you can always realize D as a quotient. L is an even lattice, then you take the dual, you form this quotient that will be a finite abelian group with a natural quadratic form on it. And every discriminant form can be realized in this way. And the lattice which you use here, that's not unique. But its signature will be unique modulo 8, and this is the signature of this lattice is called the signature of D, and this is defined well-defined modulo 8. Okay. So then we need the level of D, and this is just the smallest positive integer which kills the Q. So this is minimum. Okay, so this is the level. So, and the Y representation is now representation of SL to Z on the group ring of D. And, first, we define a scalar product here. So this is a group ring of the discriminant form. Okay, so in this way we can define a scalar product. And now we have an action of SL to Z on this thing here. So I will write SL gamma for SL to Z, and then we have these standard generators. And then gamma will act on this group ring. That's a unitary action with respect to the scalar product. And you can define it, for example, or when you know how the generators act, then you know how the group acts. So T acts diagonally. So these are the basis elements of the group ring, and T acts diagonally. So you minus here, and P round bracket X is shorthand for so standard notation. So T acts diagonally, and the action of S is more complicated. Oops. So you have the signature of E over 8, and then you have to sum over the group, and the quadratic form gives you a bilinear form. So this is the action of S, and from this representation factors through gamma n, where n is the level, and from this you can derive an explicit formula for an arbitrary matrix in gamma, but I won't write that one down. I will only give you one special case. So we suppose the level of D divides some integer n. So we take some integer n, which is divided by the level, and we take some matrix A, B, C, D in gamma 0 n. It means this C is 0 modulo n. And we can look at the action of this matrix. And it essentially shifts gamma to A gamma, to D gamma, and then you get some scalar factor. Some scalar factor which depends on some, the two adic invariant, and
because this is the Kronecker symbol.
yes. And depends on the norm. Okay, so this is the action of gamma 0 n, for example, and there's a complete formula for an arbitrary element.
I don't see what we have. E to the power D gamma.
Yeah, this is not.
D gamma.
So this is the element in the group ring corresponding to D gamma. Yeah. Okay. And so from here you see that gamma n acts trivially, because then this is 1, this is 1, and if B is 0 modulo n, this here will become 1, and D is 1 modulo n, so gamma n really acts trivially. Okay. Okay, that's a short, very short introduction to the Weil representation.
May I ask a naive question?
Yes, sure.
The very little of what I know of Weil representation realizes it in a space of functions of Lagrangian subset.
Yes.
Real valued or refinement field. How is it related? Why is it related?
So this is a special case. So the Weil representation generally gives you a representation of symplectic groups. And this here is a special case where you have the isomorphism between SL2Z and the symplectic group. So when you work out everything, then you get exactly this representation for this special case. So this is a very special case of.
I do not see the Fourier transform in this last slide.
Don't Fourier transform at all. I think for you it's better to imagine, let's consider all, so if D, the quadratic model, is discriminant form of some lattice, we consider all theta series with characteristic for this lattice, characteristic related to the discriminant group and to the dual lattice. We consider the vector of this theta series, and this is transformation of this vector. You can imagine it's like this. It's transformation of this, the vector of all theta series related to the dual lattice of original lattice A.
Yeah, this is very nice explanation. So you know this representation is very old. It describes how theta series transform. So it was known much before Weil's construction. It's probably known to Jacobi.
Oh, Jacobi, I'm not sure, but
yeah.
in the first part of 20th century it was known, yes.
Yeah, this here is essentially Jacobi's inversion formula.
For the theta series, yes.
Yes. Okay. So now the next thing, now we study modular forms for this representation. So we take a holomorphic function. This is the standard upper half plane. And we take a holomorphic function which takes values here. Okay, and if you want, you can write it. Sometimes we will write f in components. So now we say f is a modular form if it transforms with respect to this representation.
I would like to add that the order of this finite quadratic model D is exactly the determinant of the corresponding lattice, quadratic lattice. So we have finite number of generators.
Okay. So F is a modular form of weight K. So it's more or less a standard definition. The only thing is that you have to insert the representation. So you have to act with the representation on F. Okay, and we add the condition that F should be meromorphic at the cusp. So I allow finite, or we allow finite order poles. Okay. So how can you construct these functions? It's not very difficult because you know that the representation factors through gamma n. So you can construct modular forms for the bi-representation by inducing up modular forms for gamma n, and you can actually get all of them in this way. So this is the first proposition. Okay, so we have D a discriminant form of even signature. I make this assumption even signature here, but that's not necessary. It's only a technical assumption. Yeah? Otherwise, I would have to work with the metaplectic cover. And this is just a technical assumption to make my life easier. And we introduce an integer which is a multiple of the level. And we take a modular form on gamma n. Okay. And we take an arbitrary element from the discriminant form. Then we can easily write down a vector valued modular form. Oh. I'm too slow. So when you sum over the cosets of gamma n in gamma and transform or act with them on your F, and then you evaluate the bi-representation on your element E gamma, this gives you a vector valued modular form. And we also know what is important, we know explicitly what its Fourier coefficients are, because we have an explicit formula for the bi-representation. So essentially the Fourier coefficients of F are essentially, you need the expansions of small f at all cusp, and then the Fourier coefficients of F are linear combinations of the Fourier coefficients of the expansions of F at the cusp. Okay, and every modular form for the bi-representation can be obtained in this way. Sorry?
The oddity.
The oddity, that's a two-adic invariant of the discriminant form, so I don't want to explain it in too much detail, it's not very important.
And what's after slash?
That's the Peterson slash operator.
So weight
Of weight k.
Weight k. This we wrote it slash index k and m. This is the action of matrix m from SL to Z, but phi is modular. F is a modular form with respect to the principal congruent subgroup. So we have some modular form with conjugated group after all actions.
Okay. Okay, so yeah, maybe I throw out one proposition in order to save some time.
Можете это через, вот, грубо говоря, надо исследовать над двой квадратичной формой. Классификация квадратичных форм над двоадическими числами, она сложнее, чем любыми другими. Это дополнительный вариант. Да.
Yeah, so the next proposition is essentially a reformulation of the residue theorem, and it goes as follows. So if we have a modular form for the Y representation of weight 2 minus k, and I want the weight to be negative, this is not important. And we have another modular form for the dual Y representation and of weight k. So the important thing is that both weights add up to 2. Then we can pair them, and we can look at the constant coefficient of this pairing, and by the residue theorem the constant coefficient has to vanish. Okay, so then Fg bar, which is just F gamma G gamma. So this expression here, when you look at the constant coefficient of this modular form here, this will be 0. Okay, so this says constant coefficient 0, and this will be something that we will use several times later. So this is just a reformulation of the residue theorem, and there's a more...
You mean constant Fourier coefficient?
Yes. And there's a more fancy version of this theorem, which we will also use. And this is the last.
But if we take, let me say, E8 and some lattice inside E8, so I mean this conjugation, do we have conjugation if we have orthogonal complement in the unimodular lattice? If we have two discriminant forms of two quadratic forms in the same unimodular lattice. We have L1 and L2 is orthogonal complement of it?
Yes, then one of them, if you take, one of them will then transform under the dual representation.
Okay. So it means in particular we can take A1 and E7, and then correspondent representation will be dual.
Yes. Okay, so there's slightly more fancy version of this theorem, and this goes as follows. So if we have a modular form for the Y representation of weight 2 minus k, okay, then we can define a linear map which depends on this f, which goes from the space of cusp forms for the unit representation of weight k to the complex numbers, and then we just evaluate this pairing here. So G is left to G bar. And I take the constant coefficient, sorry. So we can define this map here. And this map, so this is a modular form of negative weight. And this map here only depends on the principal part of f. So it depends only on the poles of f, on the singular terms of f. And now you can ask, if you prescribe a principal part of some potential modular form, you give a principal part and you ask whether there's a vector valued modular form which realizes this principal part. Then the answer is this is exactly the case when this functional here vanishes. Okay. So that's the last theorem in this section. The modular form of weight 2 minus k is given principal path exists if and only if psi f vanishes on the space. Okay, so you can prescribe some principal part, and if this map here vanishes identically.
What type of principal part here we have? I mean, can you explain?
So, yeah, maybe. So you can write your f in terms of components, and each component is a modular form on gamma n, and it has a Fourier expansion. So we suppose, as before, the level of d divides n, then each of these components is a modular form on gamma n, and it has a Fourier expansion c gamma n q to the n over n. And the principal part is given exactly, contains exactly these terms where n is negative. This is the principal part. It contains the negative terms in the Fourier expansion.
То есть форма отрицательного веса, поэтому мироморфную часть берем от них все мироморфный кусок из разложения Фурье, вот это как бы есть главная часть.
So I can write here n and z. And the principal part is determined by the negative n here in this expansion. Okay, so now you have an idea of what modular forms for the Y representation are. Then maybe a few words on Borcherds products.
Последний результат описывает препятствие для продолжения вот этой как бы мироморфной части. То есть продолжить можно, если соответствующее вот отображение, если належит в ядре соответствующее отображение.
short reminder of what Borcherds products are. So you start with an even lattice L. Of signature n, 2, and I will assume for all my talk that this is not necessary, but I assume it here that n is greater than 2 and even. Okay. Then we can take the real vector space underlying the lattice, and we can also take the complex vector space. Okay, so these two spaces we need. Then we can define a complex manifold with two components, and these are the elements in the complexified lattice in the zero cone, and in my notation, since I have signature n, 2, this should be smaller than 0. So this is a complex manifold with two connected components, which I call H and H bar. And the orthogonal group of V acts on K, and it has an index 2 subgroup which acts. So K decomposes in two connected components. They are interchanged by complex conjugation. We choose one of the components, call it H, and on this component we have an action of the index 2 subgroup of the orthogonal group of V. Okay, and we call this subgroup OV plus. And now we intersect this group with the orthogonal group of our lattice, and this is OL plus, and we take a finite index subgroup gamma. Okay, so this is our subgroup, and then we can define a modular form for the orthogonal group of the lattice, or for gamma, as follows. It is essentially invariant under the action of gamma, and it's homogeneous of degree minus k.
То есть H — это область четвертого типа, которая в моем докладе появлялась, в докладе Винберга. Просто здесь сигнатура N2, а не 2N, как у нас, поэтому чуть-чуть другой условие.
So we have a finite index subgroup. Okay, and yeah, we also take a unitary character if we want. Okay, so and now we take a function, call it psi, which goes from H to C, and here we assume that it is meromorphic. And we say that psi is an automorphic form of weight k, or automorphic function, we are more happy with that, of weight k.
Точнее, тут H — это афинный конус на том случае.
Okay, so what do we want? We want it to be invariant up to a character value, and we want it to be homogeneous of degree minus k. Okay, maybe. So this is the definition of an automorphic form for this group gamma, maybe for gamma. And one very interesting thing here in the orthogonal case is that if psi is holomorphic, then by Köcher principle it's also holomorphic at the cusp. And there's also the smallest possible weight in this case, which is a singular weight. So this is our next proposition. So if psi is non-constant and holomorphic, then we have a lower bound on K, namely it's the bounded from below by n minus 2 over 2. Okay, and these functions which lie directly at the boundary, they are very interesting. They seem to be very rare. They have very nice Fourier expansions at the cusp because the Fourier expansions are only supported on norm zero vectors, and it seems that the singular weight cases, they are related to infinite dimensional Lie algebras. So the singular weight forms which I know, they are all the denominator functions of some Lie algebras or Lie superalgebras.
No. No. Here, the history is the following. So Freitag in 80s or late 80s conjectured that we have no modular form on singular weight. For orthogonal group. I didn't know on this assumption or conjecture, and they constructed a modular form of singular weight for unimodular lattice of signature 210. This was the latest E8. This is my additive lifting. So, and then we have modular form of singular weight of weight 4 for signature 210. But this function, certainly we can define some generalized Kac-Moody, but this is not a Borcherds form. It's symmetric, not anti-symmetric. The character is trivial.
Okay.
It's not the character determinant in this case.
Then you say, okay, in many interesting cases, these functions, the singular weight cases often correspond to infinite dimensional.
Yes, but in any case, they're very exceptional. It means it's a generalization of constant one from many points of view. Because if we write Fourier expansion, it's like Fourier expansion for the constant one in the classical case. It's why Freitag assumed that this modular form do not exist for orthogonal group. Right? My construction was a counterexample to this.
Okay. Thank you. So at least there are not many of them. In this sense, Freitag was correct. Okay. So here, what do we have? So so the weight is bounded from below. That's the important thing. Okay. And now there's a Borcherds found a nice method to construct such automorphic forms for orthogonal groups, and the idea is to generalize the theta correspondence to modular forms with poles at cusp. So that was this idea, or the idea of Harvey and Moore, and it's very roughly as follows. Okay, so we have our lattice, then we call the discriminant form of L, we call that 1D, and we take the modular form and we have to take a certain weight. So recall the signature of L was n,2, and the weight of F must be 1 minus n over 2. Okay, and we have some more assumptions. The principal part must be integral, so the coefficients which you see there must be integers. And names to the Fourier coefficients as a few minutes ago, so I call them C, gamma, this is the component, N. And I want the constant coefficient of the zero component of the vector valued modular form. I want this one to be even. These are only technical assumptions because I want to make my life easier. Okay, so essentially you have a lattice of signature n, 2 and a modular form or the bi-representation of weight 1 minus n over 2. Then you can look at the following integral. So you can take your vector valued modular form, you can integrate it against the Siegel theta function over the fundamental domain of SL2Z. So there's a problem with this integral, it will diverge, but you can regularize it in a nice way. And we call this number, we call psi of z. So the regularized value of this integral here, this gives us a function phi of z, and this function will be invariant under the orthogonal group. So this is the Siegel. Siegel theta series of L. So this is an indefinite lattice. So in order to make sense out of this theta series, you have to introduce some variable which indicates how you split off the negative definite part. And this is encoded in Z. Okay, so you can form this integral here, and essentially the Borcherds product associated to L and F is the exponential of this value. The exponential of this integral is a nice automorphic form. Nice in the sense that we know exactly where its divisors and its poles are, for example, and that it has nice product expansions at the cusp, which we can write down explicitly. This function is invariant under a subgroup here of this orthogonal group, namely the subgroup which fixes the components of F. So, and the theorem, this is the result of Borcherds. It essentially says if you take the exponential of this value, you get a very nice function. So there's a meromorphic function from H to Z with the following properties. Okay. So the first thing is psi is an automorphic form. And the weight is described as a constant coefficient of your F. And it's exactly 1/2 of this. Okay, so this is why I want this to be even, so that this here is an integer. Second, we know exactly where the zeros and the poles are. They are very easy to describe, and we also know what their order is. And the poles are described by the principal part. Yeah. The zeros and poles of psi lie at So you can look at the orthogonal complement of some vector. Yeah, so where gamma is a vector in the dual lattice, I can assume it to be primitive and of positive norm. And we also know what the order is. So you add up all the Fourier coefficients which correspond to your gamma. So C m gamma minus m gamma is weight over 2, and m is a positive integer. So this is the order of the divisor. Okay, number 3. So how is psi related to the phi, which I wrote down there? When you take the logarithm of the absolute value, this is roughly phi. And the last point is we have a very explicit description of this thing here. We can write down infinite product expansions. There is an explicit product expansion of psi at each rational, zero-dimensional cusp. Okay, so this was Borcherds. So this is a very nice theorem of Borcherds, and there's a converse theorem by Brunier which says that essentially every automorphic form whose zeros and poles are at the right position is a Borcherds product. Okay. So this almost finishes the introduction. Not quite. So now you know what Borcherds products are, and so that would be sufficient. Yeah, you know what Borcherds products are and what singular weight means. There's one more term which I need to explain from theorem 3, which is the term reflective. So I need to say a few words about that. And then there is a minor remark which is important for the classification.
May I ask a short question?
Yes, sure.
I never studied Borcherds products. Is there a nice introduction into the Borcherds? I tried to read the Bourbaki talk by Kontsevich and it didn't help me.
You can read Borcherds' original paper, or there's a book by Brunier. And
could you please write down how is it spelled?
Yes, sure. So I remove this.
Is it okay?
I don't know the title by heart, but I have
But
it.
maybe
How do you
his name
spell his
Brunier.
last name?
Only
Just
Brunier.
how do you
Just
spell
the
his
name.
last name?
Because Brunier, it's not evident in principle.
Okay.
O-U? No. Oh.
Yeah, it's this reference here. BR1. Okay, so unfortunately I have to do 2 more things. Okay, so now we know what Borcherds products are. I have to say 2 things. One about reflective forms and one about the following result which I need for the classification. So assume that we have a lattice as before and a modular form for its Y representation. Okay, and let us assume that we can write L in the form, we can write it over Z as some lattice K, and we can split off a hyperbolic plane which is rescaled by M. This means this here is a lattice, this gram matrix of this form here. Okay, and then we take a sublattice of K of finite index. Okay. What happens then? So K divided by H, K divided by M, that will be a finite abelian group, and this sits inside K prime divided, this is a dual lattice divided by M, and this sits inside M prime divided by M, and this is a discriminant form of our lattice M. So this is a subgroup of this finite abelian group, and this group here is isotropic with respect to the quadratic form, and we can look at the orthogonal complement, and this is exactly this group here. And this quotient here is isomorphic to this quotient here. Okay, so maybe since maybe this is not so important, so I make things very short. So you write your lattice L in this form, you split off a hyperbolic plane, then you take a finite index subgroup of sublattice of this K, and then you define a different lattice where you replace K by M. Okay. Now, the important point is the following. The modular form FL on this lattice here induces a modular form on this lattice in a very natural way. Okay, so FL induces a modular form Fn on n. By on n I mean for the Y representation of this lattice. Okay, and we have an embedding of n into L, and this gives an identification of the corresponding upper half planes. So Hn can be identified with the upper half plane of L. And why do I explain this? The reason is the following. So if you have a modular form on a lattice and induces in a natural way a modular form on any sublattice, and then you can look at the corresponding Borcherds products, and the functions which you get are exactly the same. Yeah, so this modular form does not contain any new information. And when you look at the corresponding Borcherds products, they also contain no more.
It's like you pass to congruence subgroup in some way.
Yeah. So
It's like old form.
yes. Yeah. So it's not. So this is a trivial way to produce new Borcherds products, and yeah, this is something you have to keep in mind for the classification later.
It's like any SL2Z modular form certainly determines a modular form for a congruent subgroup, for any congruent subgroup of SL2Z.
So yeah, so what? Okay, so if you look at the corresponding Borcherds products, then they are the same as functions. And you see this, and you calculate the expansions in one cusp, and they turn out to be the same, and then they must be equal. Okay, so this is not difficult. This is just something you have to keep in mind, that you have a trivial induction process, and this gives you many new Borcherds products which are not very interesting because they define the same functions. There's one more thing which we need, and then we can prove the first theorem, and I can promise this. Yeah, that's the first theorem. It's nice to prove. That's fun. So only a few more minutes with this definition. So that's the last definition. So we take L as above. So a lattice of signature m, 2 with discriminant form D. Okay, so now I say that an element gamma in D is reflective. So the norm of gamma must be 1 over k. And k times gamma is 0. So this must be a multiple of the order. But this is not enough. So if you have a vector which projects down, so essentially if you have a vector in your lattice which projects down to gamma, then this vector must be a root. Okay, so if there is a vector alpha which is in L and which is also in k times the dual, and it must have norm 2k. Okay, so if you have such a vector, so if it's in k times the dual, then alpha divided by k is in the dual lattice. So alpha divided by k is gamma. If you have such an alpha, then alpha must be a root.
The root means the reflection with respect to this vector is in the integral orthogonal group.
Yes, and yeah, but I need something more here. So the only way this could not be a root is that it is not primitive. So this is, if you make this assumption here, I think these two assumptions already guarantee that the reflection maps the lattice into itself. But the vector, the alpha in this case, could still be twice a primitive vector, and I want to exclude this. So the important point here is alpha is primitive. So because this is not always true, so you can write down examples where gamma is not reflective. For just take the A1 lattice. So okay, we have reflective gammas, and now we say that modular form is reflective. And the definition here is F is allowed to have only very mild poles and at very special places. Namely, the singular components can only be F gammas where the corresponding gamma is reflective. Yeah. So first we make F has weight 1 minus n over 2. So this is not. This is just so that we can apply the singular theta correspondence. Then the singular components F gamma are F gamma are F reflective gamma. So when you have singular terms here, when you have in the Fourier expansion terms of the form q to the minus n over n, then the corresponding component must be reflective. Okay, so this is one condition. Only very special components are allowed to have poles, and the poles are very restricted. And namely, the coefficient in front is 1. And the only singular terms are q to the minus 1 over k. So nothing, no higher powers are allowed. Just the smallest possible q term is allowed. So, and so we have reflective gamma, we have reflective modular forms, and I say a Borcherds product is reflective if it's a theta lift of such a function.
For us with the cooling it's vice versa. For us, Borcherds product is reflective if all divisors are reflective,
Yes.
and all multiplicities are 1.
Yeah, I will comment on this in a minute. Yeah. So this here is slightly more.
I agree, yes.
So this is more restrictive. So a Borcherds product is called reflective if it's the theta lift of a reflective modular form. So if this is the case, so a Borcherds product, a reflective Borcherds product in my definition the divisors have the following properties. So they are zeros, they have a reflective Borcherds product is automatically holomorphic, it has no poles, and the zeros are zeros of order 1, and they are orthogonal to roots. Yeah, and of course you can try to go the other way around. So you say a Borcherds product is reflective. If you take this as a definition, so the divisors are zeros of order 1 orthogonal to roots, and then you can look which kind of f's are allowed in that case. So what restrictions on your modular form do you get? And there are cases if, yeah, so this definition here is slightly more restrictive. So if you just take your definition of reflective, then you cannot deduce that f is reflective in this sense. So this here is slightly more restrictive. Yeah.
What is really the difference?
The difference is so yeah. Before I say the difference, so yeah, I wanted to have a very clean definition for reflectiveness on the level of the modular forms, because these are the objects which I can control very good. And the difference is that you might have, for example, poles when you have roots of order of length 2, for example, then I allow only terms of the I allow only poles of the form q to the minus 1 in F0, but you could also have roots of length 2 coming from these singular terms here.
I agree, yes.
The problem here is twice of this.
To have, in your case, all these roots will be really primitive.
Yes.
So it's primitive to roots. We cannot, let's say we could have, they should be primitive in the dual lattice, in some sense for you. This is primitive two roots in L, which are, and they are still primitive in the dual lattice. I think it's really this condition.
That's possible.
Yes, I think now I understand.
The good thing is, so I have many examples of reflective modular forms, and because there's something like moonshine for Conway's group, which presumably produces many reflective modular forms. And all the examples which I know, they satisfy this condition here. That's how I came up with this definition here. So this is the best definition that I found, which is simple on the level of the modular form and still contains all the interesting examples which I know. Okay, so let me just finish this here. Of a reflective modular form. Okay. In this case, psi is holomorphic and has zeros of order 1 orthogonal to roots. Okay, so the divisors have a very nice description in this case. And yeah, okay. So now we have everything which is necessary. So now we can prove the 3 theorems. And yeah, we start with the first theorem because this is essentially an exercise which is quite nice. So okay. I remove this. Okay, so this is number 4. So this is theorem 1. So we start with a unimodular lattice L. Of signature n, comma 2. Okay, and we assume that we can construct for this L a holomorphic Borcherds product of singular weight. Okay. Okay, so now, so what is the first thing that we can say? So the lattice has signature n, comma 2 and it's unimodular. Then what do we know? What do we know about the n modulo 8, n minus 2? So we know that n is 2 modulo 8. So this is the first thing that we know. Then, so this function is the lift of, so size is the lift of some scalar valued modular form. So we write this down. Okay, so our f has this form here, and we know a bit more.
Всем понятно, почему скалярная будет форма, потому что форма L унимодулярная, значит дискриминантная группа тривиальная. L со звездочкой, L двойственно совпадает с L. Значит, дискриминантная группа тривиальная, значит, у нас векторно-значная форма, которая по всем образующим, то есть по всем элементам D строилась. Это будет просто из одного элемента, так что это обычная SL2 модулярная форма. I made some remarks about why this modular form is not vector valued, but usually.
Yeah. Yeah. So okay. So and what is the weight? So by definition, this must be 1 minus n over 2. Okay. And we know. So we have some Fourier coefficients corresponding to negative m, and they must be integers. Yeah. So we have integral principal part. Okay. So, and we want to have singular weight that fixes the zero coefficient. Yeah, we know that C0 we because the constant coefficient of f fixes the weight of this thing here, and we have singular weight. That means the zero coefficient must be n minus 2. Okay, so we already know the constant coefficient. And now we can look at the largest m, or we can look at the highest pole. Yeah, so there's f is meromorphic at infinity, so this series breaks up on the negative side. So there's a largest positive m such that c minus m does not vanish. And this is called the order of f at infinity. Okay. So m infinity is the largest m such that c of minus m does not vanish. Okay. And now everything, it's very easy. So what do we do? So we introduce the Eisenstein series, or you all know the Eisenstein series of weight k. So we just multiply f with the Eisenstein series, and we adjust the weight here so that the sum of the two weights is 2. And then we know that the constant coefficient in this product here must vanish. And this is the condition we will write down. So we call that the Eisenstein series, and it's the following Fourier expansion 2k over the Bernoulli numbers, and then you have the divisor sum. Sigma k minus 1 m q to the m, and m runs from 1 to infinity. So now, so this is the Eisenstein series of weight k. And for k we choose what is a good choice here, 1 plus n over 2. So and now what we do, we just multiply these two things. F times ek. Well, let me write down pairing f.
I don't understand. K here is even, yes, for Eisenstein series.
Yeah,
but here.
So n is 2.
2 modulate. Okay.
Yes.
Yes. Okay.
So
okay,
on
okay.
n divided by 2.
Everything is okay.
Yep. Okay. So yeah, maybe I can put it here. So we now what we do next is we multiply f with ek and look at the constant coefficient. Yeah, so then these terms here will pair with the poles of this one here, and we get a contribution from the constant terms here. So we will have C0 times this stuff, and then components involving the divisor sum. So let us write this out. So what we find is 2 times k minus 2. This here is 1 times n minus 2 is this. And then we have the other terms, minus 2k divided by ek. And here we have so this is the constant term in the product. Yeah, so, and this, we know that this here must be 0. Yeah.
I'm sorry.
Yeah.
Вопрос ко всем, кто слушал, может быть, спецкурс по модулярным формам. Почему у мироморфной модулярной формы веса 2 холоморфных нет? SL2Z модулярная форма. Мироморфная, веса 2. Почему у нее постоянный коэффициент всегда 0? То, что здесь используется. Вес 2, мироморфная форма. Холоморфных нет форм веса 2. Мироморфная веса 2. Почему у нее постоянный коэффициент равен 0? Кто может сразу ответить? Подумайте на досуге. Мое указание такое, использовать дифференциальный оператор, который мы вот как раз на экскурсии изучали. Можно сказать, что все такие формы можно получить при помощи оператора, тогда все там. Да, ну, в общем, подумайте. Это очень важное свойство, что у мероморфной формы веса 2 коэффициент Фурье постоянный, всегда равен нулю. I put this exercise.
Okay. Okay, so we have this equation here. So the first thing that what we can do is you bring this to the other side, divide by 2 and multiply with bk. Then you see that k minus 2 times bk must be an integer. And we know what is very good is we know the denominators of the Bernoulli numbers. This is the von Staudt-Clausen theorem. Yeah, so let me remind you. Von Staudt-Clausen theorem, what does it say? Gives you a description of the denominator of the Bernoulli numbers. So what appears, which prime numbers to appear? These are the prime numbers with the property that p minus 1 divides k. So yeah, this is a very strange theorem. So this is the von Staudt-Clausen theorem. Okay, that describes the denominator of the Bernoulli numbers. The prime divisors of the denominator are the primes with the property that p minus 1 divides k. Okay, and now we know that k minus 2 times bk must be an integer, because here the principle, this is an integer and this is an integer, so 2 minus k times bk must be an integer. Then together with this theorem here, we find that 3 divides k minus 2, and we also know that 4 divides k minus 2, and this implies that k minus 2 is 0 mod 12. So this implies k minus 2 is 0 mod 12. So we already restricted the possible weights which can appear here just from the knowledge of the denominator of the Bernoulli number. Okay, so this is the first thing that we do. Now we know that k minus 2 is 0 mod 12. Now you know the Dedekind delta function. We take it to this power. This is an integer. And we can multiply it with our f. So this here is a modular form of weight 0. So I constructed it this way. So this is a modular form of weight 0. And can only have a pole at infinity, because this has a pole at infinity, and this is automorphic everywhere. So this can only have a pole at infinity, and it has weight 0. Okay, yeah, it has weight 0, it's holomorphic on H, on the upper half plane. So that means it's either constant or it has a pole at infinity. These are the two possibilities. And this implies that the pole order must be bigger than this here, or at least this. This gives us a lower bound on the pole order. The pole order of our f must be at least this here. Because otherwise we would have a modular form which is holomorphic everywhere, including the cusp of weight 0. Okay. So this is the second step.
But I cannot say that this proof is so simple, because first of all you use the Brunier inverse theorem. Yeah, the Borcherds product is defined by this construction, but some vector valued modular form, but this is not easy theorem in principle. So.
But when I say Borcherds product, that does not rely on Brunier's.
No, but Borcherds product for you, it's something which you get from this construction,
Yes.
but only according to Brunier's theorem, we have all Borcherds product here, more or less. For unimodular lattice, because for the unimodular lattice, his theorem is totally proved. So.
Yes. Okay.
No, if I consider Borcherds product as Borcherds product, not in terms of your definition, but what they
Yeah,
have
yeah,
Borcherds product,
Mhm.
that we have only this type of them. And the Brunier's theorem, this is the result of the whole book. So more or
Yeah.
less.
Mhm. Okay, so this is. Okay, so this is one inequality that we need. We have another inequality. And okay, so the next theorem is, we know that our Borcherds product is holomorphic, and from this we want to conclude that from this we cannot conclude that the coefficients in the principal part are all non-negatives. That's not true, but we can derive something which is similar and which is strong enough to prove the classification. So the principal part of F satisfies. So we have this sum here, Cm sigma k minus 1 and m. So we had this sum here in the Eisenstein condition in that equation there, and we can bounce this sum from below. So this
Maybe I make a remark, because
Yeah.
why this is important. Multiplicity of poles and zero is defined by some sum. So it might be that if certainly all coefficients are positive, then our Borcherds product is holomorphic. But nevertheless, we could have positive and negative coefficient, but after summation, for the order of zeros, all order will be positive. But it's some some sum of positive and negative coefficient. This is rather a special effect which we have for Borcherds product in terms of Jacobi form, or this modular form doesn't matter. So it's why classification is not so easy.
So and this, yeah, this is a nice proof which combines several arguments. So we know what the divisors of psi are. Okay, so where lambda is in the dual lattice, and in this case the dual lattice is the same as the lattice. It's primitive and of positive norm. So, and the divisor, we can write down the order of the divisor. I gave you the formula. So you just take minus m squared lambda squared over 2 and sum over all positive integers. So this is the order. And since psi is holomorphic, this is bounded below from 0, this sum. So, and now the nice thing is, we know our L is a unimodular lattice, and it splits the hyperbolic plane. And an important property of this two-dimensional lattice, this lattice has Gram matrix 1, 1, and this lattice here contains primitive vectors of arbitrary norm. That's the important thing here. So that means L has primitive vectors of arbitrary norm. Okay, and this means that these sums here, these functions, which you obtain by adding up these expressions, c minus m squared d. These functions here, which you can define for all positive integers d, they are non-negative. Yeah, that's because psi is holomorphic. So these functions are non-negative for all integers d. Okay. And now and do the rest here. Okay, so this is now just some simple calculation. So we check the sum here. Cm sigma n minus 1m. So this is by definition Cm sum over the divisors of m d to the k minus 1. Then we can change the order. So what coefficients do we have for this d? All the Cm where d divides m. Okay, that means m is a multiple of d. So we can sum over all positive integers t. And now every positive integer t can be written as a square and a square-free number. Here there's a minus here and a minus here, here and here as well. Okay, so yeah, there's this minus. So now we can write this as c. We write this t as a square and something square free. Okay, and now you see what happens. You can introduce these functions g again. Okay, so this is and now so the sum over m is just this. Yeah. Okay, and now I change the order again. And now I sum over d to the k minus 1, and the condition is that d divides m and m over d is square free. And the advantage of writing everything in this way is now that these functions here are greater or equal to 0. And this is something we can now easily bound. So this sum here, there's a minus missing here as well. C minus m sigma k minus 1 m This is equal to this sum here, and this is bounded. We can, for example, this is certainly greater or equal than g of m infinity times. So we just take one m from here, and we just take one component from here, namely when the quotient is 1. Okay. And in g infinity, there's only one term surviving, namely the highest one. This is c minus m infinity. And this here is greater or equal to 1. So this is greater or equal to m infinity times k minus 1. Okay, and that proves the last inequality. Okay. So I remove this.
But then why we have on the signature 226?
You will see that that drops out in a minute.
Oh, okay.
So we had the inequality k minus 2 over 12 is smaller or equal to m infinity. Now we take this, we take the k minus 1's power. Okay. And then we can bound m infinity to the k minus 1 from above by this sum here. And then for this we use the Eisenstein condition. We know that this is equal to k minus 2 over k times dk. This series of inequalities is what we get from what we have done so far. So note that k is 2 modulo 4 in our case, so these numbers are never 0, they are positive. So the nice thing now is this inequality leaves very little space. Yeah, so if this here is smaller or equal than this here, then this fixes k uniquely. So that the inequality k minus 2 over 12 to the k minus 1, k minus 2 over k dk. This inequality has only one solution, yeah? And this is k equal to 14. The only solution of this here is k equal to 14. And in this case we have equality. That's very nice because this fixes m as well. In this case we have equality. Okay. Okay. Okay, I make this shorter.
Then m infinity is equal to 1.
Yes, exactly. So. So I will make this shorter here because maybe it took a lot of time. So the idea is as follows. I only present the idea. So you bring everything to one side.
But maybe we can believe in this. So it's
let's do it this way. So you bring this here to the other side, and then you use there's an asymptotic formula for the bk and for the which involves factorials, and then you use the asymptotic formula for the factorials,
No,
So
we
the-
can believe in it.
Yeah, so the point is you bring this to the other side, then you see this tends to 0 for k to infinity. That means there are finitely many solutions. And then you look more precisely at it, and then you see that k to 14 is the only one. Okay? Okay, so k is equal to 14, then m infinity must be 1, and then you go back to the Eisenstein equation, then you see that c minus 1 is 1 as well. And then you know that f is of the form q to the minus 1 plus, so that if k is 14, then n is 26. Okay. So then we have 24 here plus and so on. And this is a modular form of right minus 12. So it must be 1 over delta. So f must be 1 over the Dedekind delta function. Okay, and then you know that psi is equal to phi 12. Okay. And this is the proof of the first theorem. And I will only say in words what happens for the second theorem. The idea for the second theorem is similar. What you do is you pair your vector value modular form with an Eisenstein series. Then you get a relation between the signature and divisor sum, and then you get a relation between the signature and the sum over the principal part, and then you expand this sum in the divisor degrees as we did here, and then you apply the Riemann-Roch theorem to bound the sum from below. So the delta in the general context is replaced by the Riemann-Roch theorem, and it somehow tells you that in your pairing you have to pick up a pole. This is what you need, and this is controlled, or this follows from the Riemann-Roch theorem in general. And if you work out everything in that case, then you get the bound which I gave you. Yeah, so the calculations are much more delicate in this case, but the main idea is the idea which you saw here. So that's why this proof is instructive. And then this only leaves theorem 3.
But for 3 now, certainly we have no time, but
Yes.
maybe what we're doing in our seminar, all speakers can put some PDF file with some papers, text, does not matter, some official paper or non-official text on the site of the seminar, so I can do it for yourself.
I can give you all, you can take my notes and
It's
scan
no
them.
problem, we can make PDF file and
Yes,
you
you
put
can.
them. Yes.
So we did the first 2 proofs. I also wanted to do the third proof, but I can understand that it's maybe a bit much.
Because now it's
yes, I understand.
let's say.
So if you're
Couple of
interested,
minutes.
then you look at the
Yes.
PDF slides. But
And maybe you can add also some reference to publications. Then we can in your notes, and we
yes, okay.
participants. Can
But they are
find.
not LaTeX, okay? It's only
Okay.
handwritten.
No problem. Doesn't matter.
Okay. Maybe.
But as you told us, now you have 15 examples.
Yes.
What is the largest level?
There's the largest level is 23.
23.
And
It's interesting. This is again related to 24.
the point is that you get. We can go over it in a few minutes. If you
No. I think now it will be
No,
too
not the
complicated.
others. So the the prime level, there are two different prime levels. If your vector valued modular form is symmetric, then P is 23. And if F is not symmetric, then P is bounded above by 11. And in the non-symmetric case, this number here follows from a Riemann-Roch argument, and this argument here follows from the growth of the Bernoulli numbers. So you essentially, I think you, in this classification result with the 15 examples contains everything that I know. So you need growth of Bernoulli numbers, Riemann-Roch. I put everything which I had available into that theorem, and then you get a list with only 15 reflective modular forms of singular weight. Okay, yeah, then I thank you for your patience, and I hope you enjoyed at least one of the proofs. And yeah, if you have questions, please ask.
So thank you for the talk. So please, questions. Do you have any questions? But we add some PDF file. Moreover, in MassNet, you can find, or in let me say AMS site, or in archive, you can find some number of papers of Niels, and then you can find all details of these techniques. Because our approach with Nikulin, we should present it a little bit in this seminar, related with the same technique, but we take vector valued modular form, we multiply it by vector valued theta series, and we get so-called Jacobi form. Then working with Jacobi form, we can construct also Borcherds product. Sometimes this approach, from my point of view, gives us different description of the same objects. For example, I have 24 different descriptions, different faces of this function phi 12. I mean, for one function, the only function, we have 24 different formulas for this form, and different formulas gives us very different properties of this function. So this is, you see, but phi 12, as we see from this talk, is very, very exceptional. This is the only holomorphic Borcherds product for the unimodular lattices. It's very good result. So if you have no questions, so thank you once more. And then on Thursday we have much simple talk about the wide representation of vector valued modular form, some maybe dimension formula around this, a general review with all definition of all stuff. So it will be on Thursday, 5 o'clock, exactly. The audience is 207, I think. 207. So
By whom? By whom?
The second talk, totally independent from this talk.
I
It's
could
more,
prove the last zero then.
yeah, yes, more or less an introduction in the wide representation. Спасибо всем.